Cut open an Ethernet cable and you'll find something odd. The wires inside aren't laid out straight. They're bundled into pairs, and each pair is twisted tightly around itself, dozens of turns per foot. There are 4 of these pairs, 8 wires in total, inside a standard cable. The twisting is deliberate, precise, and it's the single most important thing keeping your data intact. To see why, meet the enemy: electrical noise. Motors, power cables, fluorescent lights, even the other pairs nearby, all of them radiate interference that can scramble a delicate signal on a copper wire. A naive cable would just lose to that noise, but Twisted Pair uses a brilliant countermove that starts back at the transmitter before the signal ever leaves the sending device. Instead of sending one signal, the transmitter sends 2 mirror image copies at once. One wire carries the signal upright, the other carries it flipped perfectly upside down. This is called a differential signal. At the far end, the receiver doesn't read either wire alone. It reads the difference between them, one wire minus the other, and that single subtraction is where the whole magic trick pays off. The twist and the mirror signal work as a team. One makes sure noise lands equally on both wires, the other makes sure equal noise simply disappears. Neither works nearly as well alone. So let's slow it right down. Follow one signal from the transmitter down the Twisted Pair while noise attacks it and into the receiver, and watch the noise vanish at the exact moment of subtraction. Take 1, the transmitter takes your data and produces 2 versions of it simultaneously. On the first wire, it drives the voltage up for a 1. On the second wire, at the very same instant, it drives the voltage down by the same amount. Those 2 equal and opposite copies travel down the 2 wires of the pair, wound around each other the entire length of the cable. The actual message lives in the gap between them, not in either wire by itself. Now the interference arrives. A noise source near the cable induces an unwanted voltage on the copper, and because the 2 wires are twisted so tightly together, they sit in almost the identical spot relative to that noise. That's the crucial consequence of twisting. The same burst of noise gets added to both wires by almost exactly the same amount at the same moment. It contaminates the upright copy and the flipped copy equally. The signal reaches the receiver, and now the trick springs. The receiver ignores each wire on its own and instead computes the difference. It subtracts the second wire's voltage from the first. Split that subtraction into 2 parts. First, the noise. Since the same noise was added to both wires, it appears identically in both. Engineers call this the common mode component, the part that's common to both. And identical values subtract to 0. Wire 1's noise minus wire 2's identical noise is nothing at all. The interference the enemy worked so hard to inject simply cancels itself out in a single step. Now the signal. One wire held it upright, the other held it inverted. Subtracting an inverted copy is the same as adding it back, so the real signal doesn't cancel, it doubles. Cleaner and stronger than either wire alone. That is differential signaling in one sentence. Send a mirror pair, keep the wires physically together so noise lands equally, then subtract at the end so the noise vanishes and the signal survives. But the twist rate hides one more subtlety. Every pair in the cable is twisted at a slightly different number of turns per inch. That deliberate mismatch is not an accident. If 2 neighboring pairs shared the same twist rate, they'd line up and leak signal into each other, an effect called crosstalk. Different rates keep the pairs constantly out of step, so their fields never reinforce. Add it all up and you get an astonishing result. 2 thin, unshielded copper wires reliably carrying gigabits per second through an electrically noisy world, using cleverness instead of heavy metal armor. That's why ordinary unshielded twisted pair, UTP, is so cheap and so common. The twist does the job a bulky, expensive foil shield would otherwise have to do, at a fraction of the cost. The 8 wires and 4 pairs aren't decorative either. Slower Ethernet use just 2 pairs, one to send, one to receive, while Gigabit and Faster press all 4 pairs into service at once in both directions. The scheme has limits. If a noise source is much closer to one wire than the other, the 2 no longer see identical interference, the subtraction stops being perfect and errors creep in. That's why cables have a maximum run length. Impedance matters too. Each pair is built to a consistent 100 ohm impedance and the connectors must match, or the signal partly reflects back on itself, like an echo, and muddies the very difference the receiver relies on. This differential trick is everywhere, not just Ethernet. USB, HDMI, and the CAN bus in your car all send mirrored pairs and subtract at the far end. Once you know the pattern, you start spotting twisted pairs in every device you own. So the twist is no accident. The transmitter sends two mirror copies, the tight winding makes noise strike both wires equally, and the receiver subtracts one from the other, doubling the signal while the interference cancels itself to zero. Now you know, next time you plug in an Ethernet cable, picture those little twisted pairs quietly canceling out a storm of electrical noise you'd never otherwise beat. Follow how it all runs for more. Catch you in the next one.